Next, please let me introduce the speaker of the webinar, Dr. Bjørn Kvamme to you. Dr. Bjørn Kvamme is the Vice President of the International Methane Hydrates Research and Development Executive Committee. He has worked in the University of Bergen for more than 19 years. He has 20 years research experience in carbon dioxide storage and utilization. His research group is affiliated to the Centers for Environment-Friendly Energy Research in Norway. He has authored or co-authored for more than 500 publications with more than 4,800 citations. He is also the partner of two U.S. companies, Strategic Carbon and Hydrogen Energy. Next, let's welcome Dr. Kvamme to share his presentation.
Okay, so my name is Bjørn Kvamme, and you already heard a summary of some of my career points. I also do have distributed a bio describing the same things a bit more in detail, and also with a list of publications for the latest 6 years, and also a link to most of the papers that you can download. I also uploaded 5 papers that could be of importance for what I'm going to talk about today. The main message is that carbon dioxide is very efficient in releasing methane from frozen methane hydrates. So that means that methane is trapped inside frozen water, and these are called hydrates. Carbon dioxide will also make hydrates. So if you inject carbon dioxide into reservoirs that contain methane hydrates, they will then form hydrates and release heat during the formation. And that is the heat that is then naturally used to dissociate and release methane from natural gas hydrates. So it's a kind of a Columbi egg with many mutual benefits of injecting the carbon dioxide. You get the carbon dioxide stored very safely. First of all, this is basically the line of my career. I entered basically as a professor more or less after I completed my PhD, and I've been staying in academia for the rest of my life. But I've been working very tightly with industry, and that's something I do like, and I have been working very much with Southwest Petroleum University, and I'm very happy for that, and I'm very happy to be part of a team in Chengdu. So you have all this information in what I sent out. What I'm going to talk about today, as I mentioned, is a bit of some limitations regarding the release of methane from these hydrates. The problem is basically that very many of the pilot plant tests and very many experiments, they are basically not based on theoretical evaluation. Nothing can actually defeat the laws of thermodynamics. So you definitely need to be very considerate on how you actually release the methane efficiently. So that means that you have to use both the first and the second law, and also a combination of these, in order to understand how to best release the methane. So in summary, the first law dictates the need for the supplied heat for the hydrate dissociation. But the second law alone dictates the level of temperature that you need. And this has very often been overlooked. So I'm not going to be very detailed on the discussion of the thermodynamic equations. Paper number 2 of the ones I've included with my career is handed out. So that one will give you a very detailed derivation of all the equations. So I will briefly point to the most important things. So don't worry, you can always go back to the papers that I sent out. Is this going to be translated now or?
I'd like to translate from here. Thank you, Professor.
Yes.
首先欢迎大家来到参加本次的会议。本次会议教授将会对近6年的研究进行一个简单的总结以及汇报，其中也包括了他近几年的论文，而本次会议的主题主要包括了他近来的5篇论文，主要是关于二氧化碳，主要是关于二氧化碳的储存。我们可以通过二氧化碳来生产所需的水合物，并且在这个过程中循环利用二氧化碳。在这个过程中引入二氧化碳所释放的热量将有助于我们更好的生产钾离的水合物，并且二氧化碳可以安全的储存。并且大家刚刚也通过 PPT 看到了教授的一些详细的生平，并且教授也非常开心能够和石油大学在成都的团队进行合作。接下来我们看到了本次主要会是教授主要讲解了可能会涉及到热力学的第一定律和第二定律。第一定律主要是涉及到齐布斯自由能，而第二定律则会告诉我们所需的温度是多少，而具体的一些细节大家还可以关注教授的相关论文。
Okay.
And that's all.
So I've organized this in a way where I will first give you a brief introduction with focus on some of the controlling thermodynamic constraints on the release of methane hydrates. And then I will be much more focused in part 1 on the critical thermodynamic demands on different hydrate production methods. And in part 2, I will explain in more details, also with much calculations and experiments, why it's very feasible to use CO2 for combined storing of CO2 and release of methane. Okay, you can translate.
OK， 接下来教授将会对本次会议的内容进行了一个简介。首先，本次的会议主要有2个部分，第一个部分则是水合物的生产方式以及它所需要的热量的供应，而第二部分主要是教授将会解释为什么二氧化碳是可行的。主要从二氧化碳的储存方面，以及注入二氧化碳之后将会释放甲醇这2个方面来解释为什么二氧化碳是可行的。And that's all.
So there's one thing that is very important to understand is at least the form of the first law of thermodynamics. If you are going to release methane from the hydrates, you need to dissociate the hydrates. And the enthalpy involved in that is a function of the heat that you can supply, which is the first term on the right-hand side. And that is a heat transfer between the phases you have. You have a gas that is being released from the hydrate. You have liquid water, and you have the solid hydrate phase. And in addition, you then need to add heat from surroundings or inject heat. The second term is the mechanical work. That is not critically important, but the final term is what is called chemical work and might be very important in the process of dissociating hydrates. You can translate.
OK， 首先，在水合物的生产则是，如果我们想要从水合物中得到甲烷的话，那么我们首先要溶解水合物，那么则涉及到相关热量的提供。而我们现在的水合物当中不仅有液体水，而且有固态的水。使用相关的方法，我们将不需要从环境当中去取得过多的热量，这是第一部分。第二部分则是相关的化学作用，即使化学作用在整个过程中并不是非常重要，但是呢，我们也需要理解相关水合物生成过程中有关的化学动态。And that's all.
So if you now differentiate this enthalpy, we get the energy in watts. So now we get actually watt or kilowatts of energy consumption through heat, which is the first term. And then we also get the derivatives of the second and third parts. I will not go into details on these in the current presentation. I have this derivation in a paper which is submitted to Energy and Fuels, and I would like to discuss them at a later stage, but they are not important for this presentation. Okay, you can translate.
OK， 大家可以看到，就是这一页 PPT 当中出现了一个较为复杂的公式，这是用来计算我们在整个生产过程中所需要提供的热量，而 E 则代表了反应当中所需要的含。而具体有关这个方程的细节，教授将不在这里做出详细的讨论。大家如果感兴趣的话，可以看教授相关的论文。And that's all, Professor.
Okay. So the final term may be somewhat not very familiar to some researchers that are not specialized in thermodynamics. So very briefly, we could say that this term consists of two contributions. There is one energy contribution, which if you remove a molecule from one phase, you have to take it away from all the attraction to other molecules and put it into some other phase with new attractions in that phase. That is the energy contribution, but there is also an entropy contribution, which is the difference in the environments. When you remove a molecule, all the other molecules have to rearrange. And when the other phase gets a new molecule, it also have to rearrange. And that is an entropy contribution. You can translate.
OK. 接下来教授会简单介绍一下大家可能不熟悉的一些动力学过程，相关的热力学过程，主要分为两个部分。第一个部分则是分子在从一个项转入到另一个项当中的时候，它需要有相关的吸引能。第二部分则是涉及到相关的含变。当分子在 当分子从一项转变到另一项的时候，其周围相关的分子也需要重新，其相关分子的位置也需要重新改变、重新安排，则是相关两个部分。以上则是相关两个部分。And that's all, Professor.
Okay. So that means practically for some of the production methods, like if you reduce the pressure to outside stability of hydrate, and I'm going to discuss stability of hydrates later, then you extract water from surrounding sediments, and these might not be saturated with methane molecules, and then the hydrate will dissociate by chemical work. So the molecule in the hydrate will prefer to go into the liquid that doesn't have methane molecules earlier. You can translate.
OK， 当我们从沉积物中把水尝试着抽出去的时候，这个时候水合物当中的气压则会发生变化，往往其中的气压将会减少，因而此时水合物则会融化，并且会产生相关的温度梯度。
Okay.
Okay.
And I'm not going to details on the first and second law combined, but I need to just show it because there is no possibility of thermodynamic equilibrium for hydrates in a sediment. And that means that the usual equilibrium laws that we do know, that the chemical potential of all the components in all phases have to be the same, that is not valid anymore. But then it's the combined first and second law that tells you the composition of each phase and also how much you will have of liquid water, gas, and hydrate at any time. So there is no very simple calculation. It's simply a minimalization of Gibbs free energy. But to repeat, the details of this derivation you will find in the second paper of those I distributed. So please read that, and also feel free to be in touch with me if there's something that is very unclear. So you can translate.
Okay, thank you, Professor. 在这一部分我们会讨论第一定律和第二定律合并之下的关于水合物的一些问题。由于对于水合物在其沉积物中的热量供应是不大可能的，因此其所释放的能量可能不尽相同。在跨界面的成分组成之中，水合物分子可能极其微小，但是在水合物的计算过程中，这一方程将非常复杂。这也包含了其中所需要的吉布斯自由能。相关的细节我会在第5部分进行讨论，其中可以参考我的第2篇论文，所以希望各位能够在论文中进行进一步的探讨。谢谢。Thank you, Professor Yoko.
Is that okay?
Yeah, that's okay.
I will not actually dwell any time with this. It's basically telling some of the same as the previous slide, but this simply means that when you integrate the previous equation, it will gradually also change the direction according to that differential form. So you have to be careful even when you integrate it. So you don't have to translate this. It's supplementary information to the previous slide. So I will just continue. So what is very important here is that you can find a lot of models calculation of the enthalpy for hydrate dissociation. Many models are not acceptable. And there's another thing that is not acceptable is that people are not worried about the consistency, because Gibbs free energy and enthalpy are intimately related by fundamental thermodynamic laws. So that means that you need to actually make sure that the Gibbs free energy model and the enthalpy model are consistent and that they really obey the law that I just put on the screen here. Now you can translate.
Okay, thank you, Professor. 我们在这里所计算的，由于分子上的水合物是和水合物相关的一部分问题。根据热力学定律，它们必须保持一致性，这是因为杰布斯自由能与水合物的含相关，这也是一个热力学的问题。我们必须要确保杰布斯自由能模型和水合物的含模型保持一致，根据一些热力学的定律来进行计算。That's all, thank you.
Okay.
Okay, thank you, Professor.
So there is another aspect related to the equation I just explained. I just indicated that you have to use the minimum free energy because the equilibrium equations are not valid. And the reason is that you have too many different phases which are relevant compared to the number of independent thermodynamic variables. So basically, that is why you cannot have equilibrium, but you will have stability limits. And to the left, you have the typical stability limits of hydrate in pressure and temperature. And that means that hydrate cannot be stable if you are to the left of these curves. So the upper curve, which is in cyan, is for a very high sodium chloride in water. And the lowest curve is when the hydrate is formed from pure water and methane. So it means that to the right of this lowest curve, hydrate formed from pure water cannot exist, and to the left of it, it can form. But these are one projection of stability limits. Another projection could be the concentration of methane in surrounding water. If that concentration is too low, then hydrate will dissociate, as I mentioned before, and that's the right curve. Now you can translate.
Okay, thank you, Professor. 现在我们要讨论的另一个相关的就是，在水合物的分解过程中，将会有一个最小的吉布斯自由能，用于使在液态水中保证水合物的相关热供应。在根据独立的热力学变量，例如温度或差异的研究之中，这期间存在一种差异。这也是为什么水合物的稳定性极限与吉布斯自由能相关。在热力学稳定性极限之内，则只有温度和压力一个变量时，我们需要考虑从流入水中的水合物需要有一个最低的温度供应值。在纯水中的水合物的含一般较为稳定，但是由水产生的水合物的含，例如在进入甲烷的时候，其浓度将会非常低。That's all, thank you.
Okay. Another thing that we should keep in mind is that I'm going to show results from thermodynamic models, and that means there are models for chemical potential of water in liquid and water in hydrate, and there are chemical potential for gas and gas molecules that go into the hydrate. And when we plot curves like that to the right, we can demonstrate that the models are in accordance with experimentally measured data and that the model is correct. You can translate.
Okay, thank you, Professor. 请注意，在我们的实验研究中，热力学模型和化学式模型应该保持相一致，其中包括水以及相关水合物所组成的。在给水合物中添加气体时所产生的热量，也应该符合实验的相关数据。对于纯水热力学压力稳定性极限的水合物的相关数据，则证明了化学式与我们的实验数据相一致。That's all. Thank you, Professor.
Okay, thank you. So we can also compare the experimental data for the enthalpy of hydrate formation. And there is one example here is for the formation of methane hydrate. And there is a solid line that is calculated. There are many different experimental results. And as you can see, they are very, very different. It's very difficult to measure enthalpy of hydrate formation. You cannot really say which one of these is best because the experimental data are lacking from many, many types of information. You can translate.
Okay, thank you, Professor. 现在我们要说的是，在水合物合成中的含变以及相关的数据。在水合物的合成过程中，在实验方案里有很多的不确定性，因为实验过程有很多的变化。其热力学稳定性，我的水合物模型是唯一与热力学稳定性相一致的模型，因此在这一研究部分中，我设计的该实验可以进行相关的水合物证明实验。That's all. Thank you. Thank you, Professor. That's all.
I mentioned the thing about consistency, and I will just stress one more time on that. The thing about consistency is that the entropy of the final products when you dissociate the hydrate have to be correct. It is the same as if we think about ice. If we melt ice, we have a very well-defined change from a structured ice to liquid water, which is more chaotic. And if we evaporate the liquid water, we get an even more chaotic situation. If we don't have the entropy correct, we don't get the correct structure of the final fluids, which are liquid, water, and gas. So that is why it's very important that the enthalpy change and the Gibbs free energy change are calculated from the same model system. You can translate.
OK， 接下来我想要最后一次再强调一致性的重要程度。其意思则是我们用于计算的含变值一定要是正确的。就拿冰的含变来进行举例。如果 如果刚开始计算的含变数值不正确的话，那么我们得到最终产物的含变值也将是错误的。那么我们后续的计算也将跟着发生错误，而这也就是为什么我们在计算吉布斯自由能以及生成的水合物相关的含变时，我们应该使用相同的模型。And that's all, Professor.
Okay, thank you. So that means that we now have to make sure, as I indicated to you, that we have now the entropy difference, which we need for the energy balance in the first law. And Gibbs free energy is actually available energy when you subtract irreversibilities. So it means that we now have a consistent system between free energy and entropy, and we can expect also the entropy to be correct. You can translate.
教授的，而我的意思则是，由于含变，我们可以由第一定律看出含变的不同，并且吉布斯自由能具有它的不可逆性，因而如果分解含的计算是错误的，那么后续的相关计算也会发生错误。And that's all, Professor.
Thank you. So now we can return to the more practical issue and really focus on some production methods that have been used. And to repeat, we now have to make sure that the combined first and second law is fulfilled, and the first law have to be fulfilled. And in addition, we have to make sure that we can break the hydrogen bonds efficiently. You can translate.
接下来我们则要讨论一些实际的事情，则是相关的生产方式。在相关的生产方式中，我们必须要确保第一定律和第二定律能够同时满足。在确保能够满足第一定律的同时，我们还要确保能够有效地打破氢键。And that's all, Professor.
Thank you. So it means that we can first look at Gibbs free energy change. And if you look at the stability limits in pressure and temperature, that has frequently been used by the oil industry to see how you need to change the pressure in order to dissociate hydrate. But that is not enough. But we can have a look at that first. And in the figure to the right, we now have hydrate Gibbs free energy as function of temperature on the stability limits. So that means that you can actually change the pressure so that the stability of liquid water and gas is altogether more stable than the hydrate. But that is only one criteria. Okay, you can translate.
接下来我们可以看到的是相关的吉布斯自由能的改变，以及相关的水合物稳定性的极限。首先，我们改变水合物当中的气压，则可以溶解水合物，但这远远是不够的。结合第一定律，水合物当中的温度以及相关的其他因素也会发生改变。
Okay.
并且，and that's all.
Okay, so then we have to then also satisfy the first law of thermodynamics. And that means that we have to know that we can supply enough energy to make sure that we can satisfy the first law of thermodynamics. And as we discussed before, this can be done by adding heat, but it can also be done by chemical work, which was the third and last terms on the right-hand side of the first law. And if we now look at hydrates from pure water compared to hydrates from various degree of salt water, then we can look at the right-hand curve. But mostly for discussion today, we can focus on the black curve. You can translate.
Okay, thank you, Professor. 我们还要测试根据热力学第一定律，其供应的热量要足以保证水合物在第一定律之中所进行分解所需的热量。盐水之中的水合物不如纯水之中水合物稳定。在纯水和盐水之间的差异则会导致水合物稳定性极限的改变。Thank you, Professor.
Okay. The consistency I have discussed, so we don't need this. Any participant can read this from the handouts. So what is important is still to keep in mind that the entropy have to also be fulfilled. So the second law by itself need to be fulfilled. So we need to break the hydrogen bonds. And that means that we need a certain level of temperature. And if we try to compare this to ice, and if we want to dissociate ice or melt the ice using liquid water, it is not very efficient if we put a cube of ice and we add water which has a temperature of 1 degree Celsius or even up to 10 degrees Celsius. We all know that the ice will melt very slowly compared to a commercial hydrate production ship. You can translate.
Okay, thank you, Professor. 关于一致性的描述如图所示，其中你可以看到更为详细的解释。在第二定律之中，我们需要讨论一些氢键的问题。由于解离作用水合物的分解所产生的热量，必须能够足以有效的破坏氢键。在大多数的水合物之中，绝大部分它们自身都存在氢键，因此在液态水中比在纯水中的稳定性要更为差，这也是一个热力学的瓶颈。在液态水中所形成的水合物的过程相当缓慢。That's all. Thank you, Professor.
You're welcome.
Yeah.
So that is a problem in the literature you will find on hydrate production. You basically find curves like those on the left-hand side, where you have temperature and pressure stability limits. And if you look at the cyan curve, that is for methane hydrate. And the other curves are for different mixtures of CO2 and nitrogen. So if you follow the solid black and the cyan, just for a comparison, people are saying that to the right of the steep change for the CO2 curve, then methane hydrate is more stable. And that is not correct, because stability is determined by the level of Gibbs free energy and not by temperature and pressure, because these are independent variables. It's the function of the first and second law of thermodynamics that determines stability. And the lower free energy, the more stable. So all of the mixture of CO2 and nitrogen are significantly more stable than methane hydrate. You can translate.
Thank you, Professor. 现在的问题是，在温度和压力条件下的水合物稳定性体现。根据热力学定律，温度和压力是独立的热力学变量，它们则决定了在何种条件下特殊的水合物能够稳定存在。在水合物稳定性方面有很多差异。甲烷的水合物不如二氧化碳的水合物以及二氧化碳氮气的水合物稳定性那么好。这也是热力学定律相关的一个函数，关于水合物稳定性相关的函数。因此，在所有的成分之中，二氧化碳的天然气水合物存在的形式较多于其他两种。That's all. Thank you.
Thank you. So now we can return to one of the methods that have been very extensively tested, and that is pressure reduction. So to the right-hand side, you can see the figure for pressure, temperature, condition of hydrate. So to the left of the solid curve, then you have hydrate, and to the right of that curve, you cannot have stable hydrate. So practically, if you have hydrate without no free gas inside the reservoir, as illustrated in the figure to the left, that's a 3D representation based on seismic from a Norwegian hydrate reservoir. And you can then see that if you're pumping out water, you will get a reduction in pressure, but it doesn't mean that you get an efficient hydrate dissociation. You can translate.
好的，接下来我想要向大家讲述我曾测试过的一个重要的方法，就是压力的测试减压。我们可以从 PPT 当中看到相关水合物的温度以及压力的数据，并且我们可以看到，当我们从水合物当中抽出了水之后，气压则会减小，但是这并不代表着水合物将会完全的溶解，并且水合物当中可能也没有足够的游离气体。And that's all, Professor.
Thank you. So we do know that Japan has conducted 2 offshore tests using pressure reduction, and these have both actually froze down because the heat supply could not dissociate the hydrate for a long time. They managed to get some small production for some few days, and then it was up and down. It froze and dissociate, froze and dissociate. And after 24 days, everything stopped. And this is reported in the second paper on the right-hand side. The first pilot test, that is reported in the first reference on the right-hand side. You can translate.
Okay, Professor. 接下来则是2个相关的有关减压的实验。2个实验都是日本所进行的实验，只是2个实验都失败了，因为在2场实验中都不能够提供足够的热量，从而实验在进行了几天之后，则相关的水合物形成就被冻住了，然后相关的实验则会停止。而大家可以在教授的第2篇论文中看到更多的关于这个试点实验的信息。That's all, Professor.
Thank you. So, if you have very long time available, and if you have a huge gas reservoir in contact with hydrate, then a very slow hydrate dissociation due to chemical work will be feasible. And that means that we do have examples actually from nature that this will work, but it's an extremely slow dissociation. But to repeat, if you have huge amounts of gas below the hydrate, you have time so that the chemical work dissociation will actually make it possible. You can translate.
OK， 如果我们在水合物的分解过程中有足够的气体的话，并且我们可以等待足够长的时间的话，或许也行，因为在自然的条件下，水合物的分解是极慢的，并且相关的动态过程也是很慢的。And that's all, Professor.
Okay. So, one example of a real reservoir that has a huge gas field and a more limited hydrate cap on top, that has been producing hydrate for a long time. But it's very slow hydrate dissociation. But to repeat, as long as you have free gas below and this hydrate dissociates very slowly, then it's still enough to deliver continuously. But they even have to use hydrate dissociating things in order to keep this hydrate reservoir flowing. So they use methanol on some of the wells periodically. They have quite many wells. I think it's more than 150 wells. So some of them, they will then close periodically and add methanol. You can translate.
OK， 接下来我们则可以看到一个相关的事例。在这个气田当中，相关水合物的溶解也比较慢，但是水合物下会有足够的游离气体，并且在这个过程中，他们会加入甲醇来促进水合物的分解，并且有的时候这个油井也会时不时的关闭，加入甲醇进行相关的润滑。And that's all, Professor.
Thank you. So the reason that we can see that there has been production from the hydrate is basically that the pressure didn't reduce continuously. Actually, there was a pressure increase, and that's been very much changing. If you look at the blue curve, that is hydrate dissociated gas and natural gas. And the red curve is what the pressure would be if you only produced the natural gas below the hydrate. But you can look at the time span where you got all the pressure change. It's a very long time span, a very slow hydrate dissociation, but a very slow hydrate dissociation is feasible as long as you have very, very much ordinary conventional gas below the hydrate. You can translate.
大家，我们可以主要看一下这个图片。这个图片则展示了在具体的水合物溶解过程当中相关的气压变化以及它所需要的时长。而大家可以看出气压的变化是非常不稳定的。蓝色的这条线则代表了我们所观察到的相关的气压，而且我们可以看出所耗的时间也是很长的。And that's all, Professor.
Thank you. So, as I just mentioned, that is a production which is done slow because it's basically chemical work. And that's a slow dissociation because the molecules have to be transported from the hydrate side through an interface. That means that the hydrate is a very regular structure of water, and liquid water is very chaotic compared to the hydrate water, and these cannot be directly in contact. There will be a transition zone or an interface of gradually less and less structured water from the hydrate side until the liquid water side. And this interface is very small, but it's a very important bottleneck because the molecular transport from the hydrate to the water side is very, very slow. So you can translate.
Okay, thank you, Professor. 水合物的产生过程非常缓慢，因为这是一个化学工作。在其跨界面传输的过程中，水合物的运输存在很多问题。在与液态水接触的水合物将会在结构水上组建成一个界面，它将会在纳米的时间和空间上不停地重建自身，并且水合物在跨界面传输过程中，由于摩尔小分子所组成的界面会阻碍水合物的跨界面传输，因此更重要的是摩尔分子与水合物之间形成的界面如何有效利用并提升水合物的运输过程。That's all. Thank you.
Thank you. This is just illustrating this interface, and I don't need to spend much time of that. You can look at the densities of hydrate components on the left and right, and liquid and gas in the middle. So, but I can skip that. You can look at it on your own. So let me go to the next one. So the important thing when we are going to use CO2 for combined production and storing CO2 as hydrate, then we need to understand a bit more about how hydrate forms. And there is a lot of misunderstandings of this procedure, and the hydrate nucleation is very, very fast, but it takes long time before you get massive hydrate. And that is why you have to add different things to the CO2. You cannot use CO2 alone. So we can now look at an example which is not formation of CO2 hydrate, but formation of methane hydrate. And we have made an experimental cell consisting of a plastic container. So you can see the two half cylinders are squeezing compartments of an open space for volumes of water and methane. So if you tip this down, you get a compartment where you fill the lower half with water and the upper half with methane. So you can translate.
Thank you, Professor. 在水合物的分布密度中进行监测，可以探测到气体的极限，如图上所示。更重要的是，在水合物中注入二氧化碳，可以帮助水合物进行形成，但是该过程还存在着很多问题。这也就是为什么在不同的二氧化碳水合物之中，我们不能只选择使用二氧化碳气体添加。在二氧化碳的水合物形成过程之中，必须要保持相关参数的一致性。在这一实验里，我们没有用到塑料容器，也没有使用作为相关体积水的模型来进行实验。That's all. Thank you, Professor.
Thank you. So I'm going to show this movie, and I'm going to show you the timeline afterwards. So when you see the black regions into the original water, which is white or gray, then you are forming massive amounts of hydrate into the water phase. So this is massive hydrate time when you get these large amounts of hydrates. So if you can translate my comments to that, it would be fine.
Okay, thank you, Professor. 如动画所展示的那样，在水合物的形成过程之中，其在水中的水合物的质量传输需要一定的时间，而图上所示的是质量传输中由随时间变化的水合物的一个状态分布，其中大量的水合物将会在不同的状态下会有不同的分布，如动画所示。That's all. Thank you, Professor.
Welcome. So this means that we can look at what is called induction time, and that is the time when you get massive hydrate formation. And to the left-hand side, you just see the sampling from the experiment, and you see that it's about 100 hours before you get any significant amounts of hydrates. And that's a long time. And we also predicted the same time with my theory, and that is presented on the right-hand side curve. You can translate.
Okay, thank you, Professor. 现在是我们要讨论的是水合物的诱导时间是大量水合物开始增长的时间点。在我们所取样的水合物样本之中，水合物的形成存在于长时间水合物大量增长之后的一个过程。据我们所预测的诱导时间与实践中实际所进行的时间则是不相同的。在实验中，我们要特别注意。That's all. Thank you, Professor.
You're welcome. This is another example, not based on our experiments. The previous experiment was something I designed for a PhD student. This is an experiment that was published from a Japanese study by Tsutomu Uchida. And basically, we see that we get very good agreement with a specific diffusivity change over that very thin interface between hydrate and liquid water. So if you compare the star in the figure to the lowest curve, there is a very good match. Thank you. You can translate.
Okay, thank you, Professor. 现在则是二氧化碳水合物的相关实验。在日本进行了相关实验的模拟，但是其水合物的压缩系数在跨界面传输时的一个实验。如果你比较在盐水中的水合物相关数据以及在纯水中的相关数据，你将会得到一个更为全面的实验结果。Okay, that's all. Thank you, Professor.
Thank you. So, if we try to make a certain kind of summary, we could say that pressure reduction alone does not provide heat of sufficient temperature to break hydrogen bonds sufficiently. So it's very questionable as a production method. And it means that it will release some methane by chemical work, since when you pressure reduce, you take in other fluids from surrounding formations, and these are not saturated with methane. So there will be a certain driving force for methane going from hydrate to liquid water. But this interface I just discussed with you is a very slow barrier. So that means the transport is extremely slow across that interface. So if you don't add any heat that you do not do in the pressure reduction alone, then it's very slow. You can translate.
Okay, Professor. 接下来我们将对以上的讲解进行一个总结。我们可以看到，光是进行减压并不能够满足生产水合物所需要的种种要求，即使其中涉及到相关的化学作用，在水合物的生产过程中会产生甲烷，而甲烷又会重新融入到附近的液体水当中，并且在这个过程中会产生一个相关的界面，而这个界面的运输过程也是非常缓慢的，并且在传输的过程中界面上会产生阻碍，因而我们上述的方法并不能够提供相关反应所需要的热量。And that's all, Professor.
Thank you. Then another thing that have also been proposed and tested is to add heat. Basically, that has also been tested in Alaska many years ago. And of course, it is possible to add steam or saline water with a certain temperature, boiling or even 70 to 80 degrees could work well, but it's extremely costly. So the Norwegian company that previously had the name Statoil, but was renamed to Equinor recently, they conducted a screening of worldwide hydrates based on all the information they could get from all databases, including those from USA, and they actually concluded that it was definitely too costly and it would not be economically feasible to add heat. There is a theoretical study from China, which is published. You have the reference here. I'm not sure if this is part of a feasibility study or a standalone study, It's basically just on the flow aspect and dissociation. So there's not too much about the cost, but you can read that if you are interested. But it's too expensive as far to my opinion. You can translate.
Professor. 而我们的另一个假设，则是要通过另一个方法来提供足够多的热量，则是要么是通过蒸汽，要么是通过煮沸水的方式来提供足够的热量。但是这所有的方式都太贵了，所需要的成本都太高了。接下来我们看到的这张图片是相关公司根据美国等其他国家的相关数据库所制作出来的一张全国各地水合物相关的一个数据图。而我们可以从这张图片中再一次看到，想通过蒸汽的方式来提供水合物生产过程中所需要的热量是不太可行的。而我们也可以看，而中国方面也进行了相关的实验，我们可以在引用这里看到相关的介绍。而中国的这个测试的这个方法究竟是学术上的，还是说在实际上是可以运用的，我们还不得而知。但是它所涉及的成本要小一些，但是就我个人看来的话，相对的成本还是过高了。That's all, Professor.
Thank you. Another thing that we can do is to add, of course, things that break hydrogen bonds. We know that we can add salt if we want to break hydrogen bonds in ice outside our homes or wherever on the roads. And of course, that is possible and feasible, but it's costly. And there's a lot of corrosion problems with it. You can translate.
Okay, Professor. 而我们可以做的另一件事情，则是打破相关的氢键。我们可以通过加入相关化学盐的方式来打破氢键，但是相关的成本还是过高，并且会产生腐蚀方面的一些问题。That's all, Professor.
Thank you. Another thing that we can add is, of course, alcohols. They will also dissociate since they break hydrogen bonds in ice and hydrate. The problem is that alcohols are poisonous. Ethanol might be accepted, but methanol is very poisonous and may not be internationally accepted. But so we can look at ethanol, and to the left, we look at how the stability of hydrate change with varying concentration of ethanol in the water. And to the right, it's the Gibbs free energy of the hydrate that we form from these various concentration of ethanol. You can translate.
接下来我们还可以使用醇类来打破水合物当中的氢键，但它也有一个弊病，则是一些醇类是有毒的，就比如说甲醇，但我们却可以使用乙醇。我们可以在图表当中看到使用乙醇后的相关的数据变化，以及相关的吉布斯自由能的变化，并且它可以确保水合物具有更好的稳定性。That's all, Professor.
Thank you. So if we make a brief summary of these two things, as I mentioned, injection of salts or saline solution There is an additional problem of that. You can actually get the clogging because of mineral deposition, but that can be overcome if you do this carefully. But it's more like corrosion and different other problems that is a challenge. Methanol is very inexpensive and is being used in Russia. I don't think the general world would accept methanol being injected into the ground because of the poisonous of methanol. And another problem is that we do not know anything about the feasibility. It's probably very expensive to use alcohols. But they are efficient because they break hydrogen bonds. So production-wise, they are efficient. You can translate.
Okay, Professor. 简单的总结一下上述的内容，则是如果我们使用盐来打破氢键的话，则会涉及到相关的控化的作用，并且还有腐蚀方面的一些问题。而我们如果使用乙醇的话，乙醇的成本会过高，即使在俄罗斯这个已经有使用乙醇的例子，但是我并不认为全世界都会愿意使用乙醇，毕竟因为成本，而且毕竟乙醇会有毒。而另一个问题则是相关的可行性上的问题，即使乙醇它可以有效的打破氢键，但是它所耗的成本的确是太高了。And that's all, Professor.
Thank you. So, if you now make a summary of this part 1, the pressure reduction method is the most focused method in publications. You can find enormous amounts of experiments and pilot plants. But the problem is there are limitations in heat supply from the surroundings. And we have seen that in the Japanese test, they actually froze down. And the long-term test that was going to be for 6 months was stopped even before 1 month. And even during that time, you could see that it was temporarily freezing and releasing more gas again, freezing again. So it was an oscillating period even in the 24 days. And the problem is too low heat supply, and generally it's low temperature heat. This is heat transported due to a temperature gradient by Joule-Thomson effect, because when you pressure reduce something, and then the temperature goes down, so you get a gradient in temperature between the surroundings and the producing zone. Heat supply is very expensive, and you lose a lot of the heat just by heating the minerals, which you don't need. So I don't think that's economically feasible at all. And use of salts and chemicals that break hydrogen bonds is technically efficient, but economically, I don't know it's even feasible. And at least not with environmentally acceptable chemicals. Thank you. You can translate.
OK, Professor. 现在我们对第一部分进行一个总结。在实验中进行相关热力学的供热问题是一个挑战。问题就是在供应的限制，从周围环境中进行热供应的限制。通常来说，低温供热很难有效地打破氢键，并且这种低温供热通常非常昂贵，并且在矿物表面会有所损失。我认为这在经济上是不可行的。添加盐和一些化学成分可能是有效的，但是它在经济上是否可行， 仍然是一个问题。That's all. Thank you, Professor.
Thank you. So, the second and final part of this presentation is devoted to using CO2 in order to release the methane. It should be pointed out that there is some confusion about this method because many fundamental experiments done by X-ray and other fundamental methods that can only be used at atmospheric pressure is then done in the ice region. It could be minus 30 degrees C, so we don't have a liquid-water interface, and then the conversion is extremely slow. So this is not practically interesting, but you will find experiments from Werner Kues in Germany. He is retired now. And you will also find experiments much earlier from that from John Ripmaster in Canada. And he also did a lot of experiments with Korea. But these are at, as I mentioned, at atmospheric pressure and extremely low temperatures. So it's not interesting for real production from hydrates. So the CO2 action that we are looking at in the liquid water region and high pressure is that forming the new hydrate from CO2 that will release heat, and that heat can be used to dissociate CH4 hydrate. So another thing that is beneficial, which I will talk a bit about later, is the possibility for a stand-alone solution of production of hydrogen as the only export product. You can translate.
Okay, Professor. 第二部分则是讨论对于二氧化碳的释放能否产生甲烷的水合物的问题。在实验中，我们使用了一些矿物表面的压力参数进行测试。在矿物表面在其一定浓度的矿物表面，相关的转化过程极其缓慢。德国进行了相关实验，加拿大也从气体释放方面与韩国进行了相关的实验。在低压的条件下，我们无法确定水合物的从水中所产生的水合物是否可行，但在高压的条件下，从二氧化碳中所释放的用于水分解的热量，则无法保证甲烷水合物的生产。所以另一个问题就是对于独立溶液和注入气体的相关可能性的模拟实验。That's all. Thank you.
Thank you. So, this is something that we have studied for a long time using different theoretical methods and much experiments. And one of these is actually to do a mesoscale modeling. I will not go into details. I will be happy to send anyone papers from those studies, as well as some PhD theses. The point is that if we have a hydrate core, if we surround that by a certain layer of liquid water, and then CO2 on the outside. So the inner red core is then methane hydrate, and there is a color to indicate liquid water surrounding the red core. And then on the cyan, that is CO2, and the upper is methane, the blue one, that's methane, free methane gas. So I will then show you the picture while translating this, so you can translate this.
Okay, Professor. 在相关的实验有很多，其中之一就是在水的分子之中存在于周围的界面之中，二氧化碳的存在于周围界面的外部，因此用于甲烷所进行释放的水合物能否达到像二氧化碳那样。在图中我们可以看到蓝色区域所表示的是由二氧化碳气体中所释放的水合物已经成为了自由气体的状态，因此我们需要在相关实验中做更进一步的分析。That's all. Thank you, Professor.
So, if we then look at some of the results here, we can see that if the thickness of the liquid water is very, very thin, that's the black curve, then you get rapidly into a solid state mechanism that will work when you do not have liquid water available. The red curve is if you have 5 nanometer thickness of liquid water surrounding the methane hydrate, and the blue is if you have 7 nanometers. So when all the liquid water is consumed, then the exchange will still continue, but then it's going to a slow solid state. In real reservoirs, you have plenty of liquid water surrounding the hydrate. Hydrate saturation between 70 and 75% is considered as very good. So that means that you have more than 25% water in the pore that can be used to form a new hydrate, typically. You can translate.
Okay, Professor. 在相关的研究中，我们讨论了对于水合物形成的相关机制，在可用的水中进行的水合物生产与液态水中所相关的情况有所联系。对于所有液态水中水合物的形成，则是缓慢的过程。在原始水周边所存在的相关水分子将会被消耗，并且它其相关的转化过程也极其缓慢。That's all. Thank you.
Thank you. So there is one important thing about this injection of CO2 into natural gas hydrates. When we do experiments on this, we first have to create a hydrate, and I will show you the experimental setup in a moment. So that means we inject methane. That's the yellow and black in the illustration here. And the water is white and red. So that means the 2 hydrogens are white and the red is then the oxygen in water. And you then create a hydrate in the pores. So then we first can see why this is feasible, and after this you can translate. First of all, we can look at hydrate gives free energy to look at the stability of methane hydrate first on the top. So the free energy is a bit less than 46 kilojoule per mole hydrate. And the lower free energy, the better, the more stable it is. And if we then look at the lower curves, that is gives free energy for CO2 hydrates, pure. And the other curves are for different mixtures with nitrogen. So if we first look at pure CO2 and methane, we clearly see that the CO2 hydrate is much more stable than the methane hydrate. And Then the second question is, do we get enough heat from forming a CO2 hydrate? The answer is yes. If we look at the difference in enthalpy of hydrate formation between the CO2 hydrate, that's the lower dashed curve, and the methane hydrate, that's the upper solid curve, we see that there is in the order of 10 kilojoules per mole guest molecule, and guest molecule is either methane or CO2. So basically, per mole of methane, we have plenty of energy from the formation of a CO2 hydrate. You can translate.
Okay, Professor. 首先，我们从上一个图中可以看到，模拟的二氧化碳注入水合物当中一些微观的分子的相关变化，具体的不同分子由不同的颜色所标出，大家可以在后面细看。而接下来则涉及到，则要解释为什么注入二氧化碳是可行的。在左边的这个表格是吉布斯自由能的变化来阐释相关的稳定性。我们可以看到甲烷水合物的吉布斯自由能是相对最高的，而我们都知道吉布斯自由能越低，那么的代表着化合物是越稳定的。那么二氧化碳水合物的曲线则是更低的，也就代表着它是更稳定的，并且在加入了氮气之后，在加入了相关比例的氮气之后，它会更加稳定。那么我们则可以总结出二氧化碳的水合物要比甲烷的水合物要更稳定。而我们看到这一面的第二张图，则证明了二氧化碳水合物形成时所释放的热量足以能够用来分解甲烷水合物，因为我们可以从第二张图中看到两个水合物不同相对的含值，并且它们的差值较大，因而我们可以得出上述的结论，并且在这个转化的过程中，客体水合物不是二氧化碳水合物，则会是甲烷水合物。And that's all, Professor.
Thank you. So, then, as we discussed before, the CO2 is thermodynamically feasible, but we might want to add some component for increasing the permeability. And I will discuss that a bit more. But if we now add certain amounts of nitrogen, then the question is, do we still have enough heat from forming hydrates from a mixture of CO2 and nitrogen? So if we look at the black curves on the lower curves to the left, then the black is for pure CO2, and the black dashed curve is formed from seawater and CO2, and the solid black is from pure water and CO2. The upper curve, the red one, is for 25 mole% nitrogen and 75 mole% CO2, and forming from pure water, that is solid, and forming from seawater, that's the dashed curve. And the upper curves in cyan are for methane hydrates. And we see that even with 25 mole% nitrogen, we have enough heat to dissociate methane hydrate. You can translate.
Okay, Professor. 那就像我们之前所讨论过的那样，用二氧化碳水合物形成的热量来分解甲烷水合物是可行的，并且我们则可以想想能不能在这个过程中加入一个另外的成分，从而增加这个过程当中的气体渗透度。那么我们则可以考虑到加入氮气，但是在加入了氮气之后，二氧化碳水合物形成时的热量还足够吗？它还能提供足够多的热量吗？接下来我们则可以看到这张表格，不同的颜色则代表了加入不同浓度的氮气所涉及到的相关的含变，而通过图表上的结果，我们可以得知，即使我们加了多于25%摩尔的氮气，我们仍然可以有足够多的热量来溶解甲烷水合物。That's all, Professor.
Thank you. So we do have to keep one thing in mind, and that is that all minerals are water wetting. The only exceptions of slightly hydrocarbon wetting is if biological activity have deposited some organic material, but basically then for most reservoirs it's water wetting. And the problem of injecting CO2 is that it's a very high density fluid, and then you have to push away liquid water which is strongly attached to the minerals. If we look at the figure to the right, that is an experimental measurement of water density adsorbed on a calcite surface. And you can see that the maximum density based on oxygen is 2.4 times the density of liquid water. It's very extreme. So 2.5 for the whole water. The other peaks in this structure curve, density curve, is for hydrogen, oxygen, and for the total curve. If you model this by molecular simulation, you might find slightly higher peaks and a bit more narrow curve, but our modeling is actually reproducing the same curve, more or less. And the chemical potential of water adsorbed on calcite surface is extremely low. Means that the water adsorbed is extremely stable. It's very hard to get rid of that water and to displace it by CO2. So it means that if you have a situation of water already saturating the pores and you want to get the CO2 in, it will be a lot of resistance. And in oil terms, that means a very low injection permeability. Please translate.
Okay, Professor. 接下来我想要强调的一点就是在向水合物中注入二氧化碳的这个过程将会承受较大的阻力，并且我们可以从 PPT 上这一 PPT 上的数据中可以看到，在吸附的储存层，在矿物表面吸附储存层中，它有关的水密度是极高的，并且这也就意味着这些水是极其稳定的。 那就意味着想用二氧化碳去替换它的位置是极其不易的，并且我们也可以看到相关水的化学式也是很低的，因为我们可以总结出二氧化碳想要进入相关水合物会承受很大的阻力。And that's all, Professor.
Thank you. Another problem, which I mentioned in the second point to the left, is that when you inject the CO2, you form hydrate extremely fast, far below seconds or minutes. It's actually more or less instant on a macroscopic scale, because hydrate nucleation is a nanoscale phenomena in time and volume. So also blocking hydrate films quickly reduce injection rates of CO2. You can translate.
Okay, Professor. 如前所述，相关的二氧化碳助液气体存在了一些问题。现在要讨论另一个问题，就是在二氧化碳形成水合物的过程中，这其实是非常快的一个过程。它在根据热力学分子模拟上是一个纳米级的过程。这一现象在纳米级的时间和空间上都非常快，并且其包含了很多无法确定的可能性。其中一个就是我将要讨论的关于注入二氧化碳可能导致的化学式变化的问题。That's all. Thank you.
Thank you. So we then have to look at this in very much detail, in particular, the role of these mineral surfaces. Because even if it's very hard to get CO2 into the reservoir, we will discuss that later. We also know that CO2 to a certain extent can try to absorb on these surfaces. So water is hard to compete with, but you still manage that. So some CO2 will absorb on the mineral surfaces. And in this case, we have an illustration down on the right-hand side, where we see that CO2 from water is absorbing on hematite. Hematite is a form of rust. The most dominating rust is 2 irons and 3 oxygens, Fe2O3. And by molecular simulations, we can actually calculate this chemical potential for CO2 absorbing on the hematite surface. And we can also look at H2S, because if we are injecting CO2, there might be also remains of H2S from the separation, and that is even more aggressive in terms of competing with water in hematite absorption. The consequences for hydrate formation is something we illustrated on the top figure here. The black solid curve is stability limits for H2S and the chemical potential for that. So the chemical potential for water on that is basically the chemical potential for H2S in the hydrate is the solid curve. The chemical potential for adsorbed H2S on hematite are the circles, the black circles. And what we can see from this is that H2S will benefit in going from adsorbed state, the circles, into hydrate on that, because H2S chemical potential in the hydrate will be lower. Sorry. For CO2, the picture is a bit more different. If you look at the dashed curve, that's adsorbed CO2 on hematite, and the solid red is the hydrate. So in some region, it might look like CO2 would prefer to stay adsorbed rather than going in hydrate, but there are many uncertainties. So in summary, H2S would like to go to hydrate from adsorbed state on hematite or rust, while CO2, it's a bit mixed. Thank you. You can translate.
Okay, Professor. 对于二氧化碳在非极性的混合物中表现出非极性，在水溶液中，二氧化碳的相关注入会导致化学式的变化。二氧化碳的注入会导致水合物从赤铁矿的表面所分离，而最初水合物会吸附在赤铁矿上。对于水合物形成的浓度，这涉及到稳定性极限和相关水的化学式。对于硫化氢水合物的化学式，我们要进行进一步的实验。从进入到赤铁矿中水合物的相关变化，需要进一步被研究，因为其水合物的化学式非常低。二氧化碳在不同的注入气体中，将会导致二氧化碳吸附在赤铁矿上。对于二氧化碳水合物的形成有很多不确定的因素，如图中所示，其中黑色实线表示硫化氢水合物的相关的化学式，以及其他的相关佐证，我们有待进一步研究。关于在原位的矿物表面所进行的二氧化碳的注入，这是因为二氧化碳会在部分的剩余气体中留存，在吸附表面上的二氧化碳的水合物会导致甲烷水合物的形成，以及吸附在矿物表面的水合物的形成。That's all. Thank you, Professor.
Thank you. I will now actually introduce the next overhead, because I cannot talk on the next overhead, so you can translate when that movie is showing, because that is a very heavy movie, so it will almost kill my computer, and the sound will be very bad if I say something. So I will be silent, but the translation can be when I show the next overhead. That is showing that methane can get trapped in the water that is structured outside of the minerals. You could see all the high peaks in density of the water towards the calcite. Exactly the same thing will be with most minerals. There will be slightly differences in the density peaks, but they will be very high. And a bit distance from the mineral, then water will be able to trap methane. So I'm going to show you a movie from a molecular simulation study that one of my students conducted. So I will be silent, but the translation can be during that movie.
根据教授意思，需要在动画之间做一些解释。我们可以看到， 在矿物表面的甲烷分子会被结构水捕获，同时水会从矿物表面进入到甲烷分子会从矿物表面进入到水中。该动画是教授的一个学生用来进行展示，模拟相关在矿物表面的水合物分子之中甲烷分子的分布情况。
So what we could see from that movie, the green or green cyan almost color methane is getting density almost like hydrate density a certain distance from the surface of the mineral. You can see this density profile on the right low side, and this is definitely a density corresponding to a feasible hydrate core. The molecular dynamic simulation system is a bit small, so we would like to repeat it. I definitely need students to do that because I'm very, very busy. But I would like to set up a bigger system for students to study this for a larger system. Again, we look at the density of water as a function of distance from the mineral surface. And you can see these are from molecular simulations. You could see the experiments in the previous overhead. If you look at the peaks here, they are more narrow, for this is sample for all the water atoms. So it's actually hydrogen, oxygen, and the whole water. It's slightly thinner, but slightly higher. But the probability density, if you look at the integration of this, the result will be in perfect accordance with the interpretation of the experiments. So these densities of water make mineral surfaces impossible for hydrate to attach to. It's not possible for any hydrate water to get close to the mineral surface. They will definitely dissociate. Around these distances is where you actually get these water making hydrate with the methane, the blue and cyan-like color that you could see in the movie. So this is the distance you can also compare to here. So you get a hydrate-like core in that region here of separation from the mineral surface here to the water with methane on the outside. Please translate.
Okay, Professor. 接下来我们看到的则是在矿物表面当中，水样品的表面浓度。教授将会让他的学生就相关更庞大的系数做相关的研究，但是就这张 PPT 上的数据，我们可以看到左边的这张图，它的顶点要较高一些，并且它的两边波较窄，并且我们可以根据整张图片的变化趋势可以看出，这就证明了为什么水合物它没有办法触及到矿物的表面，因为当它触及的时候，它就会溶解。而我们也可以通过和右边的图进行对比，来得出相关的结论。And that's all, Professor.
Thank you. So, as I mentioned to you, we need to add something to increase the permeability to get the CO2 in. And adding nitrogen is a feasible choice because it is not too costly. It's fairly inexpensive relatively, but we cannot add very much. And that was a problem in the pilot study that has been done earlier. If you look at the paper on the reference to the low right, then you will see some figures here. You see a dashed curve here. That is chemical potential for water in liquid state. As long as the chemical potential for liquid water is higher than hydrate water, then definitely hydrate water is more stable. So all the solid curves, those are for hydrate water for different concentrations of nitrogen. So the lowest curve is for pure CO2, and that is, of course, always usable. Then you have 80% CO2 and rest nitrogen. So you move upward, then you will find a certain amount of nitrogen, which is a limit and the maximum amount of nitrogen you can add before liquid water gets more stable than hydrate water. So that means that we can add nitrogen all the way below the concentration that gives liquid water being more stable than hydrate water. So that is what limits this. And basically, if we study the results, around 25% of nitrogen is feasible. In this pilot test that was done in 2012 in Alaska, the Ignik-Sikumu field test, then they used something like 77 volume percent nitrogen in the CO2. So basically, they used too much CO2, and it was not possible for the injection gas to form a new hydrate. And the formation of a new hydrate, as we discussed before, is what we need. We need this formation of the new hydrate in order to make it possible to give heat for dissociation of the methane hydrate. So that means that we have to then try to do experiments according to this. And I will show you some experiments now. And we then never used that much nitrogen that was used in the pilots. So the first stages of these experiments was that we wanted to examine nitrogen maximum 30 mole percent nitrogen in mixture. The reason you had seen from the previous overhead, 30% is maybe too much, but some CO2 will dissolve in water, some CO2 will absorb, so we can try 30%, but we believe that less than that is feasible. Then we will continue and add a specific alcohol in small amounts. And the reason that we add alcohol is that it also has a surfactant effect. Because we need to solve two things. One thing is to increase the permeability, and the other thing that we need is to reduce blocking hydrate films. if you record this experiment with a hydrate film taking about 100 times before you got the breakthrough in this methane experiments, where we had water in the lower part and we had methane on top of that, and we showed you the experiments. It took 100 times before you get massive hydrate formation. And one way to reduce that is to add some surface active component. Alcohol is solvable in water, but it will still have a higher concentration towards a nonpolar phase because it has nonpolar atoms or slightly polar atoms that would like to face a nonpolar component. So an alcohol added to the water will have a higher concentration in the interface towards methane or towards CO2. An alternative to alcohol is, of course, to add a very specific surfactant in small amounts. So these are the 3 steps, and I will show you all of them, but I will first show you the experimental setup. Please translate.
Okay, Professor. 在上一张 PPT 中则提到了我们需要加入其他的一些因素来提高二氧化碳的渗透性。那我们则可以加入氮气。加入氮气不仅相对的成本较低，并且其他方面的性能也比较好。在相关的试点实验中也可以证实，大家可以看论文当中的参考，并且只要我们在考虑，那我们应考虑要加入多少氮气呢？只要在加入氮气过后，水合物中水的化学式仍低于液态水中水的化学式，那则证明化合物中水的化学式是更稳定的。大家可以在上一页 PPT 当中的图表中看到，化学式最低最稳定的时候，则是用纯二氧化碳的时候。而只要我们加入氮气的量不会使水合物中水的化学式低于液体水中的化学式则行，那么 25% 摩尔的氮气则是可行的，并在2002年曾开展过的一个试点实验，则是因为二氧化碳的量太多了，而导致水合物的形成无法正常的进行，因而在其中加入 25% 的氮气也是可行的。接下来现在我们看到的这张 PPT 教授则展示了相关的实验过程。首先我们则要收集到足够多的氮气，建议使用 20% 的氮气，或者少于 20% 也行，但由于二氧化碳会在某些条件下溶解，比如在水中溶解，其实 20% 的氮气是可以的。其次我们可以加入少量的醇可以作为表面活性剂来增加水合物薄膜当中的渗透率，并且减少相关的阻力。或者我们也可以考虑其他的表面活性剂，并且加入醇之后，水合物当中会有较高的非极性成分的浓度。我们后面也可以尝试考虑其他的表面活性剂。And that's all, Professor.
Thank you. So this is the experimental setup that I designed. I had a PhD student visiting my laboratory in Bergen, Navid Saidi, And during that period, he stayed for half a year. I designed this setup for him, and he put that into reality at University of California. So I was traveling back and forth to make sure that we made everything correctly. So there are 3 sections of the experimental cell. Those are denoted A, B, and C. The midsection B is filled with glass beads to simulate quartz, a mineral. And there is a membrane on top of A and on the bottom towards C that will not make sure that water is not penetrating and going into C. So practically, section B is only available for gases. And we then fill the water, and we can measure how much free pore volume. So we know how much water we can fill into B to fill the pores. And then for making the methane hydrate, then we fill A and C with methane. And then we can pressurize that to a desired pressure. There are 4 temperature measurements. You can see that on the left-hand side of the cylinder itself, as in the middle. So you see to the left, there is T4, T3, T2, and T1. I will show you the results from these eventually during the experiment. You can translate.
Okay, Professor. 我设计了这个实验装置，是当时为加利福尼亚大学的一个博士项目所设立的。我希望西南石油大学能够对使用这个装置作为参考。其中，第一部分是人工沉积层部分，并最初充满了液态水，并且 B 部分只对气体可用，而 A 和 C 部分是气体部分。在甲烷的注入期间 ，A 和 C 会被甲烷填充。因此，这也就决定了需要在 B 部分中填充多少水。对 B 和 C 部分可以进行加压处理，如图所示，在二氧化碳和氮气的注入期间 ，C 会被逐渐注入的气体所填充，并且 A 部分会收集到剩余的甲烷气体。我将会向大家展示我对该实验的相关研究，在这个实验装置中的一些图片。Okay, thank you, Professor.
Thank you. So, in the first part, we then make the methane hydrate in this artificial sediment. So, as I mentioned, we fill the section B with liquid water. We then pressurize sections A and B with methane, and then we sample temperatures and pressure, and we make the mass balances to look at the progress in hydrate formation. You can translate.
Okay, Professor. 第一步是需要在人工沉积层中形成甲烷水合物。我们需要注入足够的水去填满 B 部分中的一些空间体积，可以对 A 部分和 B 部分用甲烷进行加压。因此，我们在决定使用这一装置的时候，需要确定试用期来进行水合物的生产的一个模拟过程。Okay, thank you, Professor.
Thank you. So if we then just make a simple illustration, we don't need to translate this because I have explained this by words, what we do, and it's very trivial. So we just make the hydrates. So this we can just skip. Now, here we look at the samplings that we get from the sensors in the experimental equipment. These are now the temperatures. And if you look at the black and blue, those are the temperatures that is maybe more interesting to look at because we see the more massive result of the hydrate induction. So we see two peaks that corresponds to a first kind of change that you see in the peak on the right-hand side of the figure. So in particular, on the left-hand side, you see a large peak in released heat after around 3 hours. And that is the second peak. That's a massive induction of hydrate formation. And then it's more slowly further formation during the later parts of the experiment, as you can see from the pressure response on the right. You can translate.
谢谢博士。在使用实验的相关设备之中，我们可以在甲烷的生产过程期间进行一个温度和压力的监测。如图所示，左图是对温度的一个监测，右图是对压力。其中左图的蓝色曲线是第二种温度下的一个状态。需要注意的是，在诱导时间里面的第一个出现的峰值以及后面出现的一个峰值。在压力的减压的释放期间，这个过程可能会大约需要3个小时。因此，在减压的过程之中，我们需要关注的是，第二种在 T1 温度和 T2 温度之下，第二种大量的峰值出现的一个情况。Okay, thank you, Professor.
Thank you. So here are some results of this. After this experiment, we can see the pressure, and there are some data for compressibility factor and mole number distribution of methane. Before we inject the CO2 nitrogen mixture or pure CO2, as we will see also in experiments, then we reduce the pressure to close to 48 bar. And that means we extract some methane from sections A and C. We actually extract it from section A, and from C, when we inject CO2, then we remove all methane from C and put it into A. So that that is what we do from section C. So these are just some examples of what we have here in terms of mole fraction water in the hydrate on the lowest row. So the final experimental point for the making of the CH4 hydrate has a mole fraction water close to 0.86. It has slightly more water when we have reduced the pressure. So then we get slightly less methane in the hydrate. But this is then the calculated fraction of methane we then have before we start injecting the CO2. You can translate.
Okay, Professor. 关于这张表，第一列是在水合物形成结束的时候的 A 部分，第二列是在注入二氧化碳之后在减压之后的一个情况，后两列与 C 部分相似，其中 Z 是压缩系数 ，N 是摩尔数以及并且最后一行是水合物之中的水的摩尔分数。在减压的过程之中，我们需要在关注 A 部分和 C 部分之中的甲烷注入的情况。从 A 部分和 C 部分，我们可以通过移除二氧化碳，从 C 中移除 A 的二氧化碳。在压力的监测条件之下，水的水合物也可以被相应的监测。实验的一个点是需要达到甲烷水合物的形成，同时将会有更多的水的摩尔分数的变化。在减压过程中，水合物的相关变化也需要进一步的测量。That's all. Thank you.
Thank you. So here is an illustration of what is happening when you inject the CO2. So if you inject the CO2 as mentioned, then the CO2 will make a new hydrate with the free water. And as I mentioned to you, it's very hard to find hydrates which have more than 75% of the pores filled with hydrate. So there's always enough water to make a new hydrate, as illustrated on the low left. And they will then initially be there when there is also then methane hydrate. But once the formation takes place, there is heat released that will then dissociate the methane hydrate, as illustrated on the right-hand side to the low. Please translate.
Okay, Professor. 通过 PPT 上的图片，我们可以看到，在注入二氧化碳之后，形成新的水合物的一个动态的过程。并且二氧化碳会结合相关的自由水来形成新的水合物，并且我们可以看到，我们有足够的水来形成相关的水合物，并且在二氧化碳水合物形成的过程中会释放足够的热量用以溶解甲烷水合物，而这个动态的过程我们可以在这张 PPT 的右下角可以看到，而左边的图更多的是二氧化碳水合物的形成。That's all, Professor.
Thank you. So we can now go back and look at the pressure temperature profiles here. And if we look at the result, I'm not showing the result for pure CO2. I'm showing the results for 20 mole% nitrogen together with the CO2. And these are now the samplings of temperatures and pressure. So the black and blue are the lower parts temperature in the cells. So that means those closest to the bottom section C, where we have the injection gas. And the red one is that close to the original methane on the top. We should keep in mind that we keep a very high pressure in section A. That is because of saving money in the experiment. Technically speaking, there should be very limited pressure difference between injection pressure in C and A. But we keep a counter pressure, and that lowers the efficiency. So the efficiency is much better than we can expect here. But anyway, these are the responses that we get, and you can translate now.
Okay, Professor. 接下来我们看到的是相关的压力和温度的变化图，在这里将不展示纯二氧化碳的相关变化图，而展示的是20%的氮气和相关二氧化碳的温度以及气压的变化图。我们可以看到蓝色和黑色的所交叉的这条线，则是在 C 部分实验中所展示的，而红色的这一条曲线则是最初的实验所展示的，并且我们可以看到在 A 部分当中会有较高的气压，并且相关的气体的极限在 A 和 C 部分之间差距也不大，这则证明了相关实验的效率是比较好的、比较高的。And that's all, Professor.
Thank you. So, if you now look at the results from this, then to the left, we look at the moles methane released. You can look in the publication we have to see at the actual number of moles of water and methane originally in the system and how much we injected. But the important thing is the relative effects here, Dan, since you don't have the numbers up front in the slide. So the lower curve is for pure CO2, and we can see that the number of moles methane released is very low when we used pure CO2. And that is reasonable because pure CO2 then has a very low permeability, and blocking films also will reduce the performance. The dashed curve, the lower dashed curve, that is for 10 mole% nitrogen, definitely a higher performance. And then we have an dash dot. So that's for 20 mole% nitrogen. And the upper solid curve is for 30 mole% nitrogen. And as expected, there is almost no change when going from 20 mole% to 30 mole%. 25 is maybe more or less the maximum, but if you add 30%, still it might work. At least you get some exchange. But 20 is definitely the more optimum of these. On the right curve, we see maybe a more interesting curve in the sense that we see moles methane released per mole consumed CO2. So that is more like a performance. How much methane do we get out per mole CO2 we add? And definitely for pure CO2, it's a very low performance, while the performance for 20% is absolutely the optimum. 20 and 30% is definitely more or less the same. So 10 is slightly lower, but the 20% is the optimum. Please translate.
Okay, Professor. 接下来我们可以看到一些相关的结果。两张图表当中的左侧的图表则是释放的相关摩尔含的量，而不同的线则代表了加入不同量的氮气所释放的热量。而 由此我们可以通过图片上通过各个曲线的对比，我们可以得出，如果是使用纯的二氧化碳的话，渗透率将会较低，并且它会阻碍水合物的形成。并且通过观察，我们可以看出，在加入20%到30%的氮气是比较理想的，或许25%的氮气是最大的极限。但其实，如果你加入到30%的氮气的话，也可以产生相关比较理想的结果。而我们看到右边的这张图表，则是阐明了我们每加入1摩尔的二氧化碳可以产生多少的甲烷，并且通过表中各个曲线的对比，我们可以得到加入20%的氮气是产生的效果是比较理想的，或者你也可以加比20%稍微少一些的氮气也是可以的。And that's all, Professor.
Thank you. So, as mentioned, the nitrogen is mainly for increasing the permeability. The second additive that we need is to keep the interface between the gas and the water free of blocking hydrates. We do not want this blocking hydrate that can take 100 hours to break, so we need to keep the interface free of hydrate as much as we can. As mentioned, we can add alcohols because they move very efficiently together with water, and they are definitely concentrated more in the interface than they are in bulk water. So even if they're totally solvable, they will have a higher interface concentration than bulk water alcohol. Surfactants have typically a higher molecular weight. They are much more attached to the strongly to both phases, but they move more slowly. So when water tries to move to make hydrate, they're very slow in following the water movements in the interface. So on a molecular level, surfactants are stronger surfactant effects, but dynamically on molecular scale, they're a bit slow. So both of them have drawbacks and advantages, and that's why we are testing both of them. Can you please translate?
Okay, Professor. 氮气的注入是为了提升水合物形成之中在跨界面的运输能力，因此我们还需要去寻找另外一种添加剂，来保证在气体和水界面中不会渗透到水合物相关膜的阻塞。在跨界面的传输中，受到水合物相关膜的阻塞，我们可以通过添加醇的方式，而醇类则更加关注于界面传输效应，相比于关注水界面的阻塞效应。在水合物的形成物质中，其跨界面的传输是非常缓慢的过程，因此这两者都有一定的缺陷，这也就是为什么我们需要在此进一步讨论相关添加剂的一个应用。That's all. Thank you, Professor.
Thank you. So let's look at the simulation study just to indicate a bit more how the surfactant, whether it's alcohol or it's a real surfactant, then you can look at the upper figure on the left-hand side, and you see that the interface between the blue water and the yellow, which is then CO2, you can see a very sharp interface. It's very narrow interface compared to that you will have when you have added a surfactant to the system. So that is one thing. You get a much broader interface with a surfactant, and you then prevent the system from having hydrates in that interface because it's a broad interface, and the surfactant will stop any hydrate from forming because it has polar groups that will efficiently dissociate hydrates. But it will actually make hydrate easier to form inside the water phase. But then it cannot keep hydrates on the interface because of the surfactant. So it makes easier, and it's very positive for the concept that you see much more yellow in the lower left curve. You see a lot of yellow molecules of CO2 inside the blue area. So it means that there are three positive things here. A lot more CO2 goes into the water phase to form hydrate. They go faster into the water because of changes in the interfacial tension, and the higher concentration makes much more hydrate faster. Please translate.
Okay, Professor. 如图中所示，是在两种动态的体系之中的一个表面活性剂的影响。其中，如上图所示是水和二氧化碳体系，而下图是水和二氧化碳之中再加表面活性剂的一个体系。在其中，我们可以看到蓝色部分是代表水，而黄色部分代表二氧化碳。在水的界面之中形成的水合物，由于其分子作用，可能会存在一些变化。但是，水的水合物的形成通常是在界面之中的，因此可以看到二氧化碳将会更多的存在于侧面侧方区域之中。对于活性剂添加的活性剂的一些影响，第一个是它会增加界面的厚度，包括成盒体积。第二个是增加从水色界面的客体项之中的跨界面传输的质量传输。第三，它会增加在液态水界面之中客体分子的浓度。That's all. Thank you, Professor.
Thank you. So, if you now look at the time for onset of massive CO2 hydrate formation, which is the time where this exchange between CO2 hydrate and methane hydrate is really happening extremely fast, then this is the peak that we will observe also in the temperatures. And but not as much as the formation of methane hydrate, because now we are forming CO2 hydrate. The released heat is used to dissociate methane hydrate, and that consumes energy. So the net temperature peak is smaller, as we could see from the sampled data. But now we can look at how the time to reach the massive CO2 hydrate formation changes with adding alcohol or adding surfactant. So if you look at the right curve, then the circles are changes in time for massive hydrate formation from the injection gas. And we can see that the performance of the surfactant is much better, and we can get the reduction down to maybe half the time. So that means it happens double the speed as compared to pure CO2. So definitely the specific surfactant here is working better than the alcohol. What is important to keep in mind here is that these are extremely small amounts that we have added. So you can say that double the speed is not very critical when it's long times, as you can see to the left. But then again, we can add much more, and we can mix alcohols and surfactants. Please translate.
OK, Professor. 我们可以探讨添加少量的表面活性剂是否有效。例如左图中是在水和二氧化碳界面之中添加的活性剂，它能使该界面不受水合物阻塞膜的影响，同时也可以观察到大量甲烷水合物释放的时间。而右图是对于添加不同表面活性剂之中甲烷二氧化碳交换的一个开始时间，其中醇类是圆形，而表面活性剂是方形。我们可以看到水合物的形成以及涉及到相关水合物的一些变化，因此我们可以通过降低温度的方式来观察到大规模水合物转化的时间，通过添加醇类或者是活性剂。但是从图表中显示，活性剂的特性影响要好一些，因此我们在实验中是优选一些特殊的表面活性剂的。That's all. Thank you, Professor.
Welcome. So if you now make a summary, we could say that CO2 nitrogen is a feasible option. So up to 20% of nitrogen in a mixture with CO2 is feasible. Nitrogen is able to fill some of the small cavities in structure number 1. I'm not showing the structure because I expect that the audience do know much about hydrate. So it means that even dilution of the CO2 affects the chemical potential of CO2 that we need to form the new hydrate. The hydrate gets some stability that nitrogen can fill small cavities. But we need a second additive in order to reduce these blocking hydrate films. So that is an absolute must for efficiency here. As mentioned, the small alcohols have interesting molecular transport properties. And I think that the next thing I would like to do is to test mixtures of alcohol and pure surfactants. You can translate.
OK, Professor. 因而我们来进行一个总结，则是二氧化碳和氮气的混合物是可行的，并且氮气的量在20%摩尔，并且氮气可以填充相关的一些空穴。因而可以确保水合物有更好的稳定性，并在稀释了的二氧化碳当中，并且可以形成新的水合物。而我们会需要另外的添加剂去减少水合物薄膜上的阻力，并且一些小的醇类也有很好的传输性能。而我接下来也希望能够就醇类以及其他的表面活性剂相关的一些进行一些其他相关的一些实验。And that's all, Professor.
Thank you. The other points that I would make in the summary is that the experimental setup that we have now, as I showed you, is a semi-closed equipment. I want to change that to a semi-open system, meaning that we can control the pressure of injection in C, and then we can control also the pressure in A, so that that is only slightly lower than that in C. In that way, we don't get the counter pressure in A that would slow down the process, and we get a more realistic experiment, so that we can get a more realistic performance. I would also like to stress that we need higher surfactant concentrations, and that is likely to be much more efficient. We also search for environmental surfactants, and that's something we already do. So we hope to test that also in the near future. And I think it's very important to stress that theoretical studies is an extremely good tool in the search for new surfactants. Please translate.
Okay, Professor. 接下来，我想向你们展示一个半开放的实验。在这个半开放的实验中，我们可以控制 C 部分和 A 部分的气压，使 A 部分的气压只比 C 部分低一点点，并且得到更多更实际的数据和相关的实验现象。并且我想要强调的一点是，我们想要测试更高的表面活性剂浓度下的实验现象，并且我们也会在我们也想去寻找更多对环境有益的表面活性剂，而对此相关的一些理论研究也是非常有意义的。And that's all, Professor.
Thank you. So let's look at some other advantages that I also mentioned early, is that when we bring this CH4 methane, we can actually crack it using steam. Steam conversion of methane over to hydrogen and CO2 is a very old technology. It was developed in Norway. I will show you another slide. So it means that the hydrogen and CO2 that we get as products are very easy to separate because the properties are so extremely different. This steam cracking is a very major technology that is even possible to do on ship. So I think Mitsubishi published the scheme for doing this, and they do have a facility on a ship that does this cracking of methane to hydrogen and CO2. So practically, it means that if we go to this example from China that I showed you earlier, and the publication, this seemed to be very far and remote area of China. Actually, very many of the on-land hydrates in China are very remote areas. With this type of technology, we can actually then produce the hydrates by injecting CO2. We can then crack the produced methane and re-inject the CO2. Sorry, it may not even be needed that we inject nitrogen. We might even inject air together with the CO2. So that means that the nitrogen and oxygen are very close in properties. So all the results we have shown for CO2 and nitrogen mixture would also be feasible for using air instead of nitrogen. So we could actually make a standalone power generation for remote areas that does not need any supply of fresh CO2 in the long run. Of course, to start off, we need to supply CO2, but when the system is running, it produces enough CO2 by itself to deliver essentially only hydrogen as an energy product. And that can, of course, be used for a power plant, and it can be used for cars, ships, and whatever. So it's actually been examined in other projects in Norway, how you can combust hydrogen in turbines. And use it in turbines. And basically, I will not report on the results of that, but it's very, very promising. So the potential for the future is very amazing. Please translate.
Okay, Professor. 接下来我将向大家提到水合物生产二氧化碳的一些优势。我们可以通过蒸汽来裂解产生的甲烷，将其裂解成氢气和空气。这项技术已经是很古老的了，并且当初在挪威产生。我将会在其他的另一张 PPT 上解释，并且这项技术是非常成熟的，即使是在轮船上，我们也可以使用这项技术，有足够的相关的设备可以运用，并且我们在中国的一些地方也证实了相关的实验。在这个过程中，二氧化碳可以形成一个闭环，实验产生的二氧化碳可以再一次运用到水合物的生产当中，并且在这个过程中，我们可以不使用氮气，我们使用空气也是可以的。而这个过程产生的二氧化碳，从长远来看的话，我们就不用在二氧化碳的生产中再加入过多的二氧化碳。在这个水合物的生产中，并且产生的甲烷，我们可以将其用于发电，或者是用于汽车以及轮船等行业。而我在挪威所做的其他的实验，也将印证我相关的论述，并且只是暂时数据不会公开，但是相关的数据是非常的好的，非常乐观的。And that's all, Professor.
Thank you. So just a brief schematic. There are many illustrations of these cracking units. And to repeat, the technology was actually patented by Norsk Hydro around 1913. And they used this hydrogen production simply as part of the fertilizer. So they made actually then ammonia as part of the first fertilizer production. So this is still very active, and it's been modified a lot, very much to make it more efficient in terms of catalyzed for the splitting reaction. It's actually a two-step reaction where you first crack this to CO, and then the second step takes it further to CO2 from CO and further cracking. So typically the steam is injected in amounts of at least 2 to 3 times stoichiometric balance, simply to make it more efficient to have this excess steam. It's possible in the CO2 use for the hydrate production to actually also use this excess steam, but it can also be used in other ways inside the flow sheet to minimize the energy consumption. So there are possible smaller differences than the flow sheet to the right below, but it is not important for this work here. There are plenty of versions of this steam cracking procedures. So please translate.
Okay, Professor. 甲烷的蒸汽裂解技术现在是由相关 PPT 上列出的公司拥有其专利，而 Yara 是现在是一个肥料的公司，它的专利则是将氨作为肥料的一部分。大部分有效的催化剂则需要更低的温度，并且在裂解的过程中一般分为2步，会先将其裂解为一氧化氮，然后再生成二氧化碳，因而我们裂解的过程往往需要重复2到3次以达到计量学的平衡。And that's all, Professor.
Thank you. So we have already now completed the first stages of this, which was just like a small test with many limitations. So we already have planned further stages, and as mentioned, to examine mixtures of alcohol and surfactants is definitely something we want to do, and we're going to use larger amounts. We're going to balance these amounts compared to the condition we use and make sure that we have a substantial driving force for making a new hydrate from the CO2 into mixed gas. And environmentally friendly surfactants is high on the agenda. So we use molecular modeling and also partly mesoscale modeling to develop these surfactants. And it's also high on the agenda to design combined CO2 ento-swapping and steam cracking. To repeat, the concept is already well developed for the cracking. It's more like trying to make the whole combination technically efficient, and also to evaluate if all this could be made on the subsea. So subsea completion is something that we want, and I do believe it should be feasible in many places, but of course it depends on the water depth, but it will reduce the cost of the total concept extremely much. But there are many things that I would like to do, and I'm extremely happy for the collaboration I have towards China and Professor Wei's group. So I want to thank you for your attention. And I have one slide with some acknowledgements, but please translate this.
Okay, Professor. 如图所示，其中第一步骤1到步骤3是为一个博士研究的一个目标，这已成功的进行完成在2021年的12月份。也有为后续发展的更多计划，例如4、5、6步。其中第4步是去检测醇类和表面活性剂的一些混合物以及稍大的量子混合物。第5步是基于实验的过程以及相关的摩尔模型，也同样需要开发环境友好型的表面活性剂。第6步是基于二氧化碳氮气交换以及蒸汽裂解的一些概念设计，以及还有更多事情我想说的。我非常高兴能够与中国合作，以及感谢魏教授的一些支持。我也非常感谢大家的关注，并且向各位听众表示衷心的致谢。 还有一些需要进行致谢的一些单位。That's all. Thank you, Professor.
Thank you. And just some words I would like to say about the collaboration we had so far. I greatly appreciate the collaboration I've had with Southwest Petroleum University. I truly love these stays I've had in China and working with Professor Wei's group. I think it's been extremely fruitful, and I hope that we, and that's me, and also Professor Rick Coffin from Texas A&M in the United States, that we can soon get back and continue this collaboration. And what we have experienced also by all the other students and staff has been extremely positive. There's been so many people involved in making our stay in Chengdu very efficient and pleasant that there are too many to really say in detail all those names. Another thing is that this symbiosis that seemed to be with Professor Wei's group and CNOOC is also greatly appreciated. That makes a very nice bridge from what you can do on a typical university level to industrial level and maybe working towards pilot plant experiments. So that is extremely appreciated. And similar, I would mention just two persons, Professor Shou and Dr. Lee or Professor Lee. And also the hospitality from CNOOC when we have been in Beijing to discuss the projects with Southwest Petroleum University and CNOOC. And I hope that this can be a very long-term collaboration so we could put this even into real reality. It doesn't mean that I'm locked into the concept of swapping and using the CO2, but I do think it's a unique possibility. But I think that the expertise I have and the expertise at Southwest Petroleum and CNOOC are very complementary. And another thing is, unfortunately, I have a misprint in the latest sentence here, but hopefully we then can also arrange the 14th workshop of methane hydrate research and development in China. We already have the one in 2023 in Belfast. So the next one is decided to be in China, and we hope to get that done. Sorry, in 2024 in China, in Chengdu or Beijing, or maybe split it into sometime in both cities. So once again, thank you very much. Please collaborate if you want to collaborate this, to translate this as well. Okay, thank you.